Hello students. Today we are going to discuss some problems related to Newton's first law of motion. I'm going to share, I think I'm sharing my screen here, but let me share the problems that I have here. The first problem, we have four force diagrams. We have this force diagram here, this one, this one, this one, and this one. So these are force diagrams, and we have four questions related to the four force diagrams. All right, so let's take a look at each and every question and try to answer the questions. Okay, so the first question, they are asking us which one shows an object at rest. Do you think this one shows an object at rest? Or maybe this situation? Or maybe this situation? Or this situation? Now, if you think about it, object A shows that the forces are not balanced. So that cannot tell us that the object is at rest. Likewise, object B is not at rest because the forces are not balanced. And object C, the forces are not balanced. So we are remaining with a choice of D, but still, we may say that the object is at rest, but could be also be moving at a constant velocity. So to answer question number one, we would say, based on the information above, we cannot tell. Could be D, but we cannot tell. So for part A, we cannot tell. So we cannot tell. We cannot tell because take a look at problem number B. So what does B ask? Which one shows an object moving at a constant velocity? I can see that it's easy to say that D shows an object moving at a constant velocity. But as you can see, the object could also be at rest and will have balanced forces. So we cannot tell here as well. We cannot tell. We can tell. So the idea is that when there is a balanced forces, when there are balanced forces, then we are sure that the object could be at rest or moving at a constant velocity. So answer to question 1A, we cannot tell. Answer to question 1B, we cannot tell. Okay, question 1C. What is the magnitude and direction of the net force on the box in the first situation? So we want to find the net force in the first situation. So this is the situation here. Now remember, we write the net force as this. So that's the net force. And since it's in the X direction or horizontal direction, we put sub X here, and that will be the net forces. So first of all, we can put the 5 newtons. And since the force is acting to the right, it's gonna be plus 5 n newtons. And then we have to add the other force, which is the 10 newtons, but it's acting to the left. So minus there will stand for left direction, 10 newtons right here, and that will be the net force. So if you do your mathematics, you will find that this is actually -5. So -5 newtons is the net force. To answer the question fully, they're saying what's the magnitude? What's the magnitude and what's the direction? Yeah. So we're going to answer the question by saying that the magnitude is actually 5 newtons. And for direction, since we have a negative direction there, you would say left, because negative stands for left. Okay. Now, question D is asking us, okay, let's label this one as this is part C of the problem. Okay, now part D is asking us, just by looking at the force diagrams, can we tell the direction of motion of the boxes? So here are the force diagrams A, B, C, and D. If we just look at the force diagrams, can we tell the direction of motion? Well, the answer is no, we cannot tell. Just as you have seen, we cannot tell, we could not tell in this situation whether the object is at rest or not without any other information. So we couldn't tell whether the object is at rest or is moving at a constant velocity. Likewise, we cannot tell the direction of motion. Think about situation A, or object A. This object could be going to the right, for example. It might be moving to the right, but slowing down. So it's possible this can be the case, slowing down. Okay. This object A could be going to the right, or right, my right is this side. It could be going to the right, but slowing down. Why am I saying slowing down? Because there is a larger force to the left, and there's a smaller force to the right. So it could be slowing down, but going to the right. It's possible also that this object could be actually going to the left. It's possible that it could be going to the left. In this case, this could be the case if you know the initial condition of the problem, if you know any other information about the object prior to the forces acting on it. So we cannot tell right now, cannot tell. So we'll have so many examples in which, I mean, we know the direction of acceleration, but we may not know where actually the object is heading to, it's heading towards. So the answer is, let's go back to, so no, we cannot tell. As you can see, we cannot tell. We cannot tell the direction. All right, so unless we know any other information about the object prior to the forces acting on it. All right, okay, so let's move on to the other question here. So we have a metal bar, so a metal bar support here. And me put this, the metal bar, and we have a scale right here to read 800 newtons scale, and we don't know how much force is right here, but we have a box weighing 500 newtons, another box or crate weighing 400 newtons acting downwards. That's the weight. The weight is acting downward, and the metal bar itself weighs 400 newtons here. All right, so the question for us is what should be the tension of force in this rope? What should be the tension of force in this rope? All right, this problem relates to the condition for equilibrium. The condition for equilibrium. As you can see, the two crates or boxes and the metal bar are at rest. In other words, they are all in equilibrium. So talking about the box I'll try to indicate the box here, another box here, and the metal bar here, they are all in equilibrium. So for that reason, I can use the condition for equilibrium to find out the missing force right here. So the condition for equilibrium tells me that, so this is we'll call this static equilibrium. So the sum of all forces, right now we have all forces acting in the y direction. So I'll put a y here, must be equal to 0. So that's the condition for equilibrium. And then I will go ahead and write down the expression for the net force in the y direction. So remember, we'll have one force that is 800 newtons. Here, that's the tension in this rope, the tension in this rope, read by the scale over there. So I'm going to say that's plus 800 newtons. So plus 800 newtons. The plus indicates going as acting upward on the system of objects of interest. And then we have the 500 newtons acting downward. That's acting downward. So I'll put minus 500 newtons. Okay. The next one is the weight of the metal bar itself. That will be plus negative 400 newtons. And then we're not done yet. We have to now move on to this weight. So that will be plus, open bracket, negative 400 newtons. And we have also this force acting on the system of interest. That's the tension force here. We don't know how much that is. So that force, maybe just, we don't know how much it is. So we know for sure some, so I'll make a small arrow because I anticipate it's gonna be smaller, some reasons. All right, so how about that? So I'm going to add the question mark. Let's just say question mark because we don't know how much that is. The result must be 0. Okay, so I have taken care of all the forces and equal to 0 because of the condition for mechanical equilibrium. All right, so let's try to add up all this. So we have 800 minus 500 minus, we can deal with these together because they are all subtracting. So I'll end up with the net force in the y direction will be equal to actually 800 newtons. I'll drop the plus sign because we know it's 800 newtons plus 800, same thing. Now this line here indicates that they are all negatives, 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 negatives. So maybe I can just add them up, all of them. So 500 plus 400 plus 400, that gives me 1300. So that gives me 1300 newtons. Yeah, 1300 newtons plus question mark. The answer must be 0. Okay, and then I go down here. I look at this problem. I'm looking for question mark, but I can also deal with this part. 800 newtons minus 1300. What am I going to get? That will give me, what's the difference? 500. To give me 500 newtons, but with a negative sign, because this is the minus here, 1300. So the difference between the two has to be computed, and the difference between 800 and 1300 is 500. With the sign will be the sign of the larger number, it's minus here, so minus. So plus question mark equal to 0. And therefore, you can tell here, we can add both sides of the equation by 500 newtons, and that will help us to find our question mark. So question mark will be plus 500 newtons. So we actually, the scale here will read 500 newtons. So the scale here will read 500 newtons. Okay. All right, so that's it. We just applied the condition for mechanical equilibrium, or the condition for equilibrium, and that's what we get there. All right, so let's look at question number 3. Question number 3 says, identify significant forces that act on a cell phone at rest on a smooth, flat surface. So I usually draw my smooth surface by just having a line and putting these lines to indicate it's a surface. And I put my cell phone somewhere there. So this is my cell phone, here, cell phone. Okay. Well, yeah, cell phone. And then I have to draw all the forces acting on the cell phone. Right now, obviously, we know there is gravitational force acting on this. So there's this force acting down. So we call that force sub G, that's force due to gravity. And there is also what we call a normal force, or some people call this one a support force. So I'm going to use F sub S. So this is the support force. That's the force due to the surface on the cell phone. That's F sub S. And these forces are actually really significant because the sum of these forces must be equal to 0. If I try to sum up all the forces in the y direction, the answer must be 0. In other ways, positive support force plus minus Fg equal to 0. So make sure you put a minus here to indicate it's acting downward. So basically, this tells you that the support force is actually equal to the gravitational force. All right. So these are the significant forces that keeps the cell phone at rest or in position at the same location. We are saying that these are significant because there might be some, air force due to air. The air might be blowing around here, maybe, if there's some air blowing, maybe the wind, some external force that very insignificant, very, very tiny. Those ones can create a little bit of static friction, but we are not concerned about those. Those are very, very insignificant. We can ignore those. All right. What about question B? Question B, 3B says that if a brief horizontal force is exerted on the cell phone slides and then comes to a stop. Does this observation goes against Newton's first law of motion? Well, Newton's first law of motion tells us that an object in motion or an object in motion at a constant velocity will keep doing so unless an external force acts on it. So since it's a smooth surface, it might be that once you set, let me go back. Since it's on the smooth surface, it might be that once you give it an external force, like this one, if you give the cell phone that kind of force, you know what's gonna happen? Since it's a smooth surface, it will kind of start moving towards this direction. So there will be some velocity there, okay, velocity. Well, it's a smooth surface, so we anticipate that the cell phone will be kind of moving at roughly at a constant velocity initially, right? So you give it a brief force and then you stop pushing it. We see the cell phone moving at a roughly, I'm emphasizing this, that's roughly constant velocity. Approximately, maybe I should say, constant velocity initially. But as by experience, no matter how smooth the surface might be, eventually the cell phone will slow down. Does that go against Newton's first law of motion? The answer is no. We still know that friction cannot be 100% negligible. So there is some friction that will slow down the cell phone. It cannot slide forever. All right. So in this case, no. I mean, we're not violating any law here. Okay. So the cell phone slows down due to friction. The cell phone slows down due to friction. One thing you must know is that as the cell phone is moving, this force is no longer acting. This force stops to act because it's a brief force. The only force acting whilst the cell phone is moving is the frictional force. It is, it is small because it's on the smooth surface, but over time, the small frictional force will slow down the cell phone to a stop. Okay, let's move on to look at question number 4. Question number 4, they say you exert a horizontal force of 600 newtons in order to slide a heavy crate across the floor at a constant velocity. So there is actually a comma here. In order to slide a heavy crate across a floor or the floor at a constant velocity. So I'm seeing this problem as similar to the one we just finished. So this is the problem here that we have here. This is the problem. And then you exert your force here, which is about 600 newtons. Yep. So how much is the force of friction between the crate and the floor in relation or in comparison to the pushing force? So the hint here is constant velocity. If the box is moving at a velocity that is constant, then we are sure that there are balanced forces acting on the crate. Balanced forces means that your force diagram will look like this. Is the object. This could be the pushing force, and the frictional force will be acting here. If this is 600 newtons, this must also be 600 newtons in order to achieve the constant velocity situation. So frictional force is also 600 newtons. Otherwise, the box will slow down. If frictional force is less than, if I should say, here we have balanced forces, and then we have the box moving at a constant velocity. But just for your information, the moment we have unbalanced forces, the box will be accelerating, and accelerating can imply slowing down or speeding up. So we don't want to have that. So the moment we have one force being smaller than the other, then we are going to have an acceleration. All right. So that is the case when, for example, I was about to say that, but I got stuck a little bit. But that is the case when you have a box like this. If you have your 600 newtons force and the frictional force maybe let's say 200 newtons, this case will end up with acceleration. And acceleration means that the object is moving at changing speeds or changing velocities. All right, so these are the questions I wanted to share with you. If you have any questions, please let me know. Let me know. These are the questions I wanted to share with you. So I'll also share these questions somewhere. I'll let you know as a document with solutions. Maybe you might find it useful to have this document together with what I was trying to do here. What was this? We cannot. Okay. All right, thank you so much. If you have any questions, please let me know. Bye.